Assalamu alaikum and welcome back. We're continuing with our lecture series on the special theory of relativity. And once again, I want to bring 2 points to your attention. First, to reiterate, the first few lectures are really just about the physics. I know many of us are itching to get to the Quran, but number one, I think that even without any Quranic verses at all, as Muslims concerned about science and the universe, we should try to understand relativity because it was truly revolutionary. Number two, I think that our approach in this course is to try to be rigorous and in-depth. That means rolling up our sleeves, really getting into it, and once we get some genuine understanding, then we take that and use it to enhance our appreciation of the Quranic verses. So please bear with me and do not be in any way frustrated by the fact that we're going to dig in right now. And in fact, I hear from a lot of people that their criticism about science and Quran lectures in general is that they just don't go in depth enough. I know a lot of us are really hungry for some real science. So we're going to take a little bit of a simplified approach to relativity, but not too simple. In fact, it'll really try to present it as it is. And to start us off and get us in the right frame of mind, this is one of my absolute favorite quotes by Einstein, that things should be made as simple as possible, but no simpler. And we will try to make relativity as simple as possible, but no simpler, so that we can get a genuine understanding. So let us now begin then by looking at the radical consequences of the notion that the speed of light has to be the same for all observers regardless of their state of motion, different than a baseball, as we have said before. And to do that, we're going to use what is called a light clock and do a thought experiment, similar to the types of experiments that Einstein did. And again, these were thought or conceptual experiments, but since then, special relativity has been verified time and time again in the lab. And the idea is, imagine that there is a clock that works this way. A light source sends up a pulse of light, it is reflected in a mirror and then reflected back to a detector, and every time that happens, the clock ticks 1. That's 1 unit of time. Now, we're going to imagine that this light clock is seen from 2 different frames of reference. First, it is on a spaceship and you're on the spaceship, and so the light goes up and the light comes down and the clock ticks 1 time unit. For you, of course, because you are on the spaceship, that light clock is stationary. It is not moving. It is just as if you have a cup of water on an airplane. The water doesn't slosh around if there's no turbulence. For you, that cup of water is stationary. For a guy on the ground, that cup of water is moving at 500 miles an hour. Now, from the ground, the person on the ground sees the pulse of light being emitted, but then when it is received on the top mirror, the spaceship has moved. And then when it is reflected back again to the bottom mirror, the spaceship has moved again, and so the pulse of light actually traces this path rather than goes straight up and down. Now, to understand the consequences of this, let's review together something that I'm sure many of you remember from school, which is the Pythagorean theorem, and it is the relationship of the lengths of the legs of a right triangle. And I know that a lot of you can recite this in your sleep, that a squared plus b squared equals c squared. So if we have a right triangle, then the length of one leg squared plus the other leg squared is the length of the hypotenuse squared. And this Pythagorean theorem will be very important in what's to come. And an example of a right triangle is a triangle that has this leg 3 and this leg 4, And then we know that the hypotenuse will be 5 because 3 squared, which is 9, plus 4 squared, which is 16, equals 5 squared, which is 25. That is an example of an easy right triangle that illustrates the Pythagorean theorem. Now let's get back to our light clock. And again, we're going to do a tiny little bit of math here, but we will take it nice and slow and do it all together. So the light beam travels up and travels down for the stationary observer, and let's say the length here is L. It travels a length of L up and back. So as far as the stationary observer on the spaceship, the guy for whom the light clock is not moving, so this is you on the spaceship with the light clock, you see the light go a distance of L up and L down, that's 2L, and we divide that then by the speed of light, which is c, and that is the amount of time that has ticked, right? Because time is distance over velocity, or velocity times time is distance, right? So if you take the distance you travel divided by the speed, that gives you how much time it took. Like you travel 60 miles an hour. You travel 60 miles at a speed of 30 miles per hour. Then you divide 60 by 30. That means it took you 2 hours, for example, to make the trip. Now let's look at the situation from the guy who was on Earth watching the light clock on the spaceship. For him, remember, the light traverses this triangular path. And so it goes this way and then this way. And if we call L the leg of a right triangle, and this is, again, the length of time, TB will be the length of time that it takes for observer B for the light to go up and to come down. Observer B is the guy on Earth. That means this whole distance is the velocity of the spaceship times TB, right? The time that it took for the light to go up and come down. So this distance is only half of that, so it is V times TB over 2. So now we have 2 legs of a right triangle and the hypotenuse h. And for the guy on Earth, TB has to equal the distance that the light travels, which is h and h, over the speed of light, which has to be the same for all observers, so it would be 2h over c, but we see that h is the diagonal or the hypotenuse of a right triangle. One leg is L, one leg is V, the velocity of the spaceship carrying the light clock, times TB over 2. So by the Pythagorean theorem, h squared equals L squared plus V TB over 2 squared. This leg squared plus this leg squared equals that squared. And that's why we need the Pythagorean theorem. And so this will be the time elapsed from the point of view of the guy on Earth. I hope you're still with me, and I hope you're not frustrated. We're going to keep going now. So this is the diagram we were just looking at, and we're saying that for observer A on the spaceship, the time for 1 tick of the clock is 2L over C. For the guy on Earth, it is 2H over C, because the light travels H and H instead of L and L. Now, let us look at this. We're going to take TA and we're going to square it. So TA squared is simply this squared, which is 4L squared over C squared. TB squared is just this squared. So if you square this, you get 4H squared over C squared. Now, let's look at this Pythagorean theorem right here. We're going to just subtract minus VTB over 2 squared. And when we square that, we get this, and we subtract it from h squared to get L squared. So L squared is h squared minus V squared TB squared over 4. Simply have the L squared by itself and make it h squared minus this squared. Now we're going to substitute what we know. We know that TA squared is 4L squared over C squared. But L squared is h squared minus V squared TB squared over 4. So we're just going to take this quantity and put it in here for L squared, so that we can write TA squared as 4 times this expression for h squared, for L squared, forgive me, over C squared. So I'm just rewriting this, but substituting for L squared this expression. Then we just simply slightly rearrange. We bring the 4 in, we multiply through, we divide each one by C squared, and so now we get that TA squared is 4h squared over C squared minus V squared TB squared over C squared. One more now. So we were just saying that TA squared is 4h squared over C squared minus V squared TB squared over C squared. Let's remind ourselves, TA squared is 4L squared over C squared, TB squared is 4h squared over C squared from the previous slides. So this term right here is just TB squared. So now I'm going to put TB squared in here, and I get TA squared is TB squared minus V squared, TB squared over C squared. Now I'm going to factor out a TB squared, and I'm going to get that TA squared is TB squared times 1 minus V squared over C squared, where again, C is the velocity of light, V is the velocity of the spaceship. And finally, I'm going to divide by this term, both sides, to get that TB squared is TA squared over this. And then I'm going to take square roots, that TB equals TA over the square root of 1 minus V squared over C squared. Now let's look at what we have done. What does this tell us? This tells us that the clock here, measured by observer B. Remember, observer B is the guy on Earth. His time, what he sees, is the time that the guy on the spaceship, observer A, sees, divided by square root of 1 minus V squared over C squared. This number here is always less than 1. We can't have a negative thing in the square root. It's 1 minus some velocity less than the speed of light over the speed of light. So we're dividing this by something less than 1. When we divide TA by something less than 1, we see that TB will be bigger than TA. This factor here, this square root, the square root of 1 minus V squared over C squared, is the single most important factor in special relativity. And what that tells us is that the clocks don't measure the same. Time runs differently. Clocks tick differently between a stationary observer and a moving observer. This is revolutionary. In the world of Newton, in the world of Galileo, in the thousands of years before Einstein, nobody imagined this. We would think that if I have an accurate clock and you have an accurate clock and I am flying in a plane or a spaceship, 5 seconds is 5 seconds. It doesn't matter that I'm in a spaceship and you're on Earth. Time is absolute. We just move through space and through time. What special relativity is saying is that no, time is actually different. It ticks differently for the guy who is moving versus the guy on Earth. And what the guy on Earth sees is that there's a time dilation, that the time, as far as he is concerned, is TA divided by this factor less than 1. That means that there is a time dilation for him. He sees the world of the guy on the spaceship as running slower. He thinks that the clock of the guy on the spaceship is running slower than his own clock because as he measures the ticks of the clock, he sees that compared to the guy on the spaceship, that the ticks have a longer time interval. And so there is a difference in the way time runs between a stationary observer and a moving observer. Once again, a completely revolutionary view of our universe. Nobody imagined that time actually runs differently if you are standing still or if you're moving. 5 seconds is not 5 seconds. You will measure 5 seconds. I will measure something different if I am standing still and you're moving. I think that's enough for this lecture, more than enough. We will explore a little bit more the amazing implications of this in the next lecture, inshallah. Assalamu alaikum.